Hello, in this short little video we're going to talk about how to design a buffer. So, you're going to use the Henderson-Hasselbalch equation to design the buffer because this is the easy way to talk about buffers. And here's what you want to do. So when you're looking at this, the ratio of acid to base determines what the pH of the buffer is. So given a certain acid, you'll have a certain pKa, and then you can play around with the relative amounts of the acid and base to change the pH somewhat. Now, the actual values of acid and base determine the buffer capacity, and so buffer capacity is defined as how much strong acid or base the buffer can neutralize. It's usually good if you can neutralize more strong acid or base, but sometimes it depends on other things that you want to do, so it is something you should at least consider when you're designing a buffer solution. So yeah, a good buffer solution, your acid and base are in the ballpark of equal so that you can absorb a good amount of either strong acid or strong base. And they're fairly large. You have a high buffer capacity. Sometimes that runs you into problems because then you have a pretty high ionic strength of your solution, like a high amount of salt, and sometimes that can mess things up. Like you can precipitate proteins out of solution with a good amount of salt, so you have to worry about that. But okay, so then here's how you can work the math on it. So say you want to design a buffer system with a pH of 3.6. Well, and you have these three choices. Which one are you going to pick? Remember, buffers work best when you're in the ballpark of the acid pKa, and we gave some arbitrary limit of plus or minus 1 pH unit from the pKa. So if we want pH 3.6, then we want a pKa closest to 3.6, and of these three choices, that's formic acid. Seems to be my favorite example for these slides. Go figure. Okay, so then, well, now we plug the numbers in like this. We know what pH we want. We know the pKa of formic acid. And then we can solve for this ratio of base over acid. So you can rearrange this to have some number equal to the log of base over acid. Then to get rid of the base 10 log, you take 10 to the thing on the left side and the right side, and then you get this, what's on the screen. And then that's equal to 0.72. So now, if you want this pH, all you need is your base to be 0.72 for every one acid you have. And remember, this is the conjugate base of the weak acid. You're adding both to make the buffer. And so, 0.72 and 1 is one possibility. As long as you keep this ratio, you can scale the absolute amount and still keep the same pH. All right, so now here's one for you to try. I encourage you to pause it, and then I'll put the answer up. All right, so now you want an acetate buffer with a pH of 4. So what molar ratio of sodium acetate to acetic acid should you use? And here's the Ka. Here's the equation, the Henderson-Hasselbalch equation. Now we're going to need to know pKa, so let's find that. And then we can plug the numbers in. We want a pH of 4 on the left. And we're almost at the edge of the reasonable pH range for this buffer, right? Because 3.74 is the arbitrary limit, the lower limit we would set for this. So we're still within that, so that's okay. Do the math. And then we get 0.18 for this ratio. Now, one possibility we could use is have 0.18 molar sodium acetate, the base on the top, and have 1 molar acetic acid on the bottom. And as long as you keep this ratio, you can scale that however you'd like. So if you're asked to do this as a problem, what's the molar ratio? The easy way to do it is, if this number is less than 1, just set the acid to 1 and then put that number on the top, right? So we said 1 molar acid and 0.18 molar base. If your number is bigger than 1, then just set the base equal to 1 for a simple example, and then make the acid less than that, and then 1 divided by something less than 1 will give you a number bigger than 1. So that's all I got. Thanks for watching.